Today we will be discussing Lab 5, where you explore your own adventure. In this lab, I will be using Tracker to observe the motion and energy of a basketball being tossed up vertically and then falling to the ground. Using Newton's second law, initial data from Tracker, and energy principles, we will also be able to construct a GlowScript code predicting the motion of the basketball and the energy involved in the system. The force of the hand will give off a non-zero initial velocity, and the forces acting on the ball after will be gravity alone. In this lab, we will also be able to calculate the kinetic and gravitational potential energy throughout the video, using physics principles and GlowScript code. Here we can see the Tracker video. The ball will go vertically up and then fall straight down to the ground. Tracker will collect the data for you. Looking at this diagram, we can see the physics principles involved with the energy conservation in this lab. After the ball leaves the hand, it has an initial velocity and initial kinetic energy. This kinetic energy must equal the gravitational potential energy working against the ball. After the basketball reaches its maximum height, the energy is calculated afterwards, mg times the total height the basketball fell, plus 1/2 mv final squared to represent the kinetic energy involved. We can solve for initial velocity using kinematic equations that we learned earlier in the semester. We use mgh equals 1/2 mv squared to solve for the velocity. Tracker is able to give the maximum height y position, in this case 0.910. Plugging this value in, we get the initial velocity of 4.223 meters per second. We will use this in our GlowScript initial conditions. As we set up our code, we input the ball's mass, its initial position vector, which is centered at the origin, the velocity that we calculated, gravity, and j hat, the vector 0, 1, 0. Continuing on with our code, we are able to initialize system energies using physics principles. In this lab, we're including kinetic energy, gravitational potential, and total energy for the purposes. Under the calculation loop, we can also calculate Fnet, hence implementing Newton's second law to update the position and the velocity of the ball throughout its motion path. Furthering on in the code, we will update the energies as well. This code is set up to graph the change in energy, hence using the graph we are able to see if the law of conservation of energy is upheld. Lastly, in the code we update the clock and the code repeats itself. The predicted position of the basketball will also be graphed in this code. In this graph we can see the change in energy. The total energy, which is represented by the orange line, remains at 0, which means the energy conservation was upheld. For every gravitational potential energy, there is either a negative or positive kinetic energy that cancels it out. In this graph, we can see the observed versus predicted position. The graph is somewhat off. We can explain this by maybe a possible drag force not being implemented into the lab. And these very things are our conclusions. The intersection in the energy graph displays the moment the ball tips from the maximum height and begins to fall downwards. The gravitational potential energy hits 0 and becomes negative, while as the kinetic energy increases positively, keeping the conservation of energy intact.